Hey guys, so this is the final video that I will be doing today, and it will be the problem set from, oh, tired guys, the problem set from last week's lesson on kind of the basics of transformations and inverting matrices. So the thing that I wanted to start out with was a little bit on inverting matrices and an important theorem. So this would be problem number 13. So you're supposed to prove that a 2 by 2 matrix A, where you've got A, B, C, D, is invertible if and only if AD minus BC cannot equal 0. So the way that you do this, and this is something that I had to talk to Dr. Prudhomme about, is that you use the identity matrix. And what you say is you set A, B, C, D, that's a 1, 0, 0, 1. And this is like your basic rule for all inversions. Like anytime you're trying to invert a matrix and find the inverse, you use this idea of setting it equal to that. So basically there's, we've got the whole arithmetic process, which I will run us through just for the sake of it. So the first thing that you're going to want to do is, in this case, is to take one, let's see, what are you going to do first? You're going to divide by A, right? So that would lead us to 1 B over A, 1 over A, 0, C, D, 0, 1, which we can then take that and say, let's see, 1 B over A, 1 over A, 0, and then we can say, 0 here, once we cancel that out, but once we cancel that out, that means that this would change to CB over A equals C over A of 1, which would then turn into 1 B over A, 1 over A, 0, AD minus BC over A. Sorry, this should have said CB over A minus C over A. It's really hard to see what I'd written down here for arithmetic, but you should end up with this right here, with negative C over A1. Then from there, we can say that yes, from there we can extrapolate out to this final product, which would be us figuring out this here. So we would, if you're curious, which you should already know this from like our basics of matrix algebra, but if you're curious, we would multiply this out to get 1 here, and then we would get rid of the variable here. So we would have B here and 0 here, and the stuff on the side would change obviously as a result of that. So the final answer that we end up getting is 1, 0, 0, 1 A over AD minus BC minus B over AD minus BC over negative C over AD minus BC A over AD minus BC. So this does in fact prove that, because what we can then do is we can pull out 1 over AD minus BC times A negative B negative C D, right? And so if that is the case, then that means that if AD minus BC equals 0, anything over 0 is going to not exist, right? So that makes that frankly impossible, or non-existent. So that brings us to a really important theorem that this problem set brings up for us. the important theorem being that you should have 1 over AD minus BC times in here. Let me grab the book because the book has it written out in a very clear way that's easy to understand. So if A, B, C, D is invertible, then you have to be able to write it as A, B, C, D to the -1. Sorry, y'all. Down here, this should say D and this should say A, by the way. So if that's true, then 1 over AD minus BC times D negative B negative C A should equal A, B, C, D inverse. So that formula really just gives you a basic rule. And it also reminds us that anytime we want to find the inverse, we have to use this identity matrix over here on the other side to be able to figure it out. So that problem, we will do a couple of other short ones. And then we'll be done because I'm not going to spend a ton of time on this. I know I spent a lot of time on the notes for this week. I'll just kind of give you some basic gists here, really. So the next one that I want to talk to us about is number 37. So in 37, it wants us to consider a linear transformation from R2 to R2. Now, we're first going to remember, of course, that the reason why this is this R2 to R2, in case you've forgotten, is if we've got n times m as our matrix times n. So if we've got n times m times n times 1 equals n times 1 and vice versa, we could do it the other way around too. The point is that this here, so we've got 2, like the n and the m both equal 2. So in other words, 2 variables, 2 rows. But I just wanted to remind you of that. So basically, what it wants us to know is we've got vector w, vector x, and vector v. Okay, so what it wants us to know is it multiplies it by some transformation t. And you end up with t of w, t of x, t of v. So basically what it wants you to know, or what it wants you to figure out is whether or not, so you've got these two vectors, v and w, right? V and w, that are on this line, and x is another vector whose endpoint is on the line segment connecting the endpoints of v and w. So it wants to know, is the endpoint of vector t of x on the line also on the line segment connecting vector t of v and vector t of w? So this seems so straightforward, right? Like, why would this not be on the endpoint just like this is? But it really wants you to figure out how to write that. And so this was kind of one of the things I had to talk to Dr. Froome about, because I was like, this seems so simple. Of course it's on the same line segment. But really what he explained to me is that a linear transformation warps space uniformly, right? So x is really vector v plus k times vector w minus vector v. What I mean by that is w minus v would be that, right? So vector x is really just if you subtract these two and you multiply that by any scalar and then you add vector v, right? Because if you subtract these two, then what you're left with is this. Right? It's this. And then if you add vector v to that, is how you end up with your x. But what you like the way that you figure out that it's still going to be on the line segment is that if we have t of x equals, sorry, so we have t of v plus k times t of w minus t of v, right? You know, if we reason through this, we realize that we can like look at these two different we can look at these two different equations and say that, you know, if the only thing that changes is just this, right? And also, you know, we can distribute this, so we can have t of v plus k times t of w plus k times t of v, which means we could also say t of v plus t, well, we can just keep it that way, but if the basic idea is that we've still got this format, we've just got the t, you know, the t of v out front. I mean, like I said, a linear transformation warps space uniformly. And what that means is that when one of these you know, if this transformation applies to one of these things, it applies to all of these things, right? And so there's still the same relationship between them. And a linear transformation doesn't change that, and it can't change that because a linear transformation warps space uniformly. And that was kind of what Dr. Prudhomme pointed out to me. So you can take this equation, and even if you know, have t of x, t of, you know, even if you have a transformation, you know, it affects all of these things. And so they're still all going to have the same relationship to each other. So that's how we know that t of x is still going to be connected to this line segment. The last thing that I would like to do really quickly is a super basic, is a much more basic problem, which should be nice because if you've noticed in this video, I've often had to stop and think about what I'm talking about and then keep going, which I hope hasn't confused y'all too much. It's really just helpful for me to kind of stop and look and reflect, and then I kind of realize what I'm talking about and pick up my train of thought. But if we've got V1, V2, all the way to Vm, they're arbitrary vectors in Rn. If we have a transformation from Rm to Rn, which is given by T of x1, x2, all the way down to xm, that equals, you know, x1, V1, x2, V2, on and on to xm, Vm. It wants to know, is the transformation linear? And this is really easy to figure out because all we have to say is that we know that this is going to become V1, V2, Vm times x1, x2, xm. And we're familiar with this because this is in the ax equals b form, right? And that's how we know that something is linear. So I just wanted to remind us of that. That's just kind of a really basic idea that we learned from the last chapter. So, you know, just to recap, what we thought about was a couple different things. We thought about a couple main ideas. The first one, when you're trying to find inverse, you use this idea and then switch everything around to find inverse. 2, if something is invertible, it has to have 1 over AD minus BC of D. Let's see. Or what was it? I believe it was DBC negative A. That should be it, yes. So something can only be invertible if it follows this form, and this is true for it. Third thing, space warps. Transformations warp space uniformly. That was the third thing that we reminded ourselves of and talked about. And the very last thing was we just reminded ourselves of the form A is equals B is linear. And we will often have to try to prove things linear by getting them into this form. So that was just kind of a couple of the problems from the problem set from last week. This is a wrap on the videos for today, which would have been about 7. I don't know. I lost count after like 3. So I hope that you have enjoyed them all, or the ones that you chose to watch, or the ones that you skimmed, or the ones that you looked at and then didn't watch. But I hope they all gave you pleasure in some way or another. And I will be back next week to talk about the problem sets for this lesson, and then also probably a lot of the chapter of next week.